All right, well, good afternoon. Welcome to the ISL Colloquium. And it's a pleasure today to welcome Professor Cedric Langbort from the University of Illinois, Urbana-Champaign, who's currently on sabbatical at Berkeley, who's not so far away. And Cedric is very well known for his work on control theory, with a certain game theoretic, economic, and stochastic flair. He's won the IEEE Career Award before coming to Urbana. The NSF Career Award. That's what we were frowning for some reason.
No, I got that one too. I just didn't know that one. That's all.
And Cedric, before going to Urbana, was a postdoc at Caltech, a PhD for now, and undergrad in Chicago.
Oh wow, you remember that?
I learned it, yeah. Cedric, welcome.
Thank you very much, Sanjay, for the introduction, and thank you everyone for having me here. I realized that I should have called this the ISL Colloquium, not seminar, so I apologize for that. So the work I'll be talking about today is related to cybersecurity of control system, and I'll get into that just in a short bit. I have to say that this is joint work with my brother Abhishek Gupta, who's co-advised by Professor Bashar and myself, and also by a good friend and colleague of mine in Australia, Professor Valerie Grunovsky, who's at the UNSW in Canberra, even though Canberra is not in South Wales. Anyways, but first, if you let me, I'll give you a plug, my 1-minute plug, which is that you may have noticed that I did not say that I'm affiliated with aerospace engineering or electrical engineering or anything like that. I'm claiming that I'm affiliated with the Center for People and Infrastructures. And so that's the plug. What is that center? It's a new center we've started at CSL, within CSL. What's interesting about it is that we're trying to put together not just engineers, but also artists, social scientists, human-machine interface designer to try to answer questions of interface design between people in the system that are nominally meant to serve them, but sometimes actually use the people to their own advantage. And that's what this little logo of ours is supposed to capture. Let's take that to infrastructure. And you understand why my sabbatical is at Berkeley. And I'll just leave it at that and say that if you want to know a little more about the projects we're looking at and the general framework for this work, please check us out. So that was the plug. Okay, so let me go back to the actual topic of this talk, which is cybersecurity of control systems. I don't know if there is a lot of motivation to be given for people in this room. But if there were, I should say that the motivation for this work is this Chinese-speaking thermostat, by which I mean, or what this is supposed to refer to, is an attack that took place in 2009. I think that was in the Department of Commerce, where it was realized that basically thermostat had been hacked into, right? I mean, more recently as yesterday, other things have been hacked into, but they're not control systems, right? They're just databases. I won't say anything about that today. I'm really interested into problem security and control systems. And you may wonder, okay, what's the big deal hacking into a thermostat, right? It's just a thermostat. Well, there are two things. Immediately, if you are a person who makes a thermostat, like Honeywell or people like UTRC, United Technology, you know what thermostats sometimes are used for. Yeah, what does the Chinese ideogram mean? That's a good question that I don't know.
Last character. It's a simple one. Oh. I think it's martial arts.
Martial arts.
Okay. All right.
So I guess the motivation
You know
is...
simple one.
Yeah,
No.
I'm Chinese.
I know, okay. But you don't. You guys don't.
I recognize.
Okay.
So martial arts?
Yeah,
Yeah.
Okay. That's always the thing. I should have checked that wasn't an insult.
Right.
That's a
right.
total waste of money.
Exactly. Exactly. Right. So, I mean, thermostats sometimes are used for pretty critical systems. For example, in the microprocessor industry, where you have to make sure that temperature is kept within very clearly defined bounds, otherwise you're losing a lot of money, and that can be fairly critical. But more importantly, more to the point, this is an example of attacks taking place purely at the cyber level, purely hacking into a network, purely hacking into data, and disrupting the ability of the control system to do its job, which is to close the loop and ensure stability and all performance. And as the Internet of Things is only growing, this type of security breaches is becoming more and more, I guess, worrisome. So that's really the motivation for this work. As a lot of you probably know, we've come to know a lot within the control community about network control systems in the past decade. We have a fairly good understanding of how effects such as packet drops, delays, finite bandwidth, and so on and so forth can affect the stability of the system, can affect your ability to meet the performance requirements that you have. But all of this is in a network, is in the framework of an imperfect yet non-strategic network, right? You have a packet dropping channel it's not malicious, it's not strategically trying to drop those packets, it's just dropping packets. You have finite bandwidth, not allocated in a way that's strategically designed to hinder your ability to control the system, it's just limited bandwidth, right? The type of problem that I want to talk about today are cases where you're controlling over a network, fine, but that network is actually strategic and is actively trying to perturb the control task that your controller is trying to perform, right? And unfortunately, relative to innocuous network control system problems, we know not that much about it within the control community. So this talk is about trying to talk about this, specifically focusing on some models of denial of service attacks, by which I mean not an attacker trying to crack open a packet and modify what was contained in that packet, but actually blocking the passage of the control input to the plant, right? And I'll stay at a very simple level because you'll see that things can get hairy quite fast already. So in the sense that it will be, LTI systems, sometimes scalar systems even, right? But I'll try to be rigorous, and in particular I'll try to say something about how information structure matters, and of course I'll get into game theoretic formulation fairly quickly. And most importantly, if you just want to take one thing out of this talk, it would be this. The question I'm trying to elucidate in this talk, or to wrap my brain around, is what does an adversarial channel look like in a network control system scenario? In particular, is it anything like the innocuous networks that we know, or not? And if it's not, is there anything we can do about it? That's really the question I'm asking. And so what I'll do is I'll start with two very simple models that hopefully I'll convince you are very natural. I'll study the gain that come out of these models, and we'll get very different predictions out of those two models. And then I'll stop, scratch my head, and wonder, why is that? And can I somehow, by taking a slightly more theoretical, abstract view, understand why the predictions are so different, and go forward with it? Okay? So let me start with what I guess you could think is the simplest, not trivial model you would think of as a control theorist trying to understand this kind of problem. So I give you a scalar LTI plant, right? And with a little process noise, because why not? So the scalar, right? Everything's scalar. And what's different here is your B matrix, what would normally be your B matrix, is an alpha K, which is a control input under the control of an attacker. The attacker can decide to stick the B matrix to 0 or 1, right, and can do so probabilistically. So the strategy of an attacker will be a map from the state of the plant to 0, 1, and can be a randomized map, right? You can choose 0 with some probability, 1 with some probability. Okay? Of course, if I let my attacker do that at any instant of time with no constraint, what we'll do is just block everything all the time, not that interesting. So I have to put some kind of constraint on the number of times your attacker can attack. And that you can capture in several ways, but again, I'm after something fairly simple. So I'm going to put a constraint on the number of times the jammer can jam in expectation over an n-step horizon. And this is this constraint, so this means that the jammer can, in expectation, jam m exactly n times out of n, with m less than n of this, right? So that's really what the attacker is trying to do. And this is the cost function that the attacker is trying to maximize, and the jammer is trying to maximize, and the controller is trying to minimize. So I have a quadratic cost here, again, as simple as can be, because it's everything scalar, so I pay this price. And notice here that I've just decided, because it will make things a little simpler for now, that the attacker pays only if the input reaches the plant, right? If alpha is 0, the U that was sent over the network doesn't feature in the cost, right? So that means that I pay a price not for creating the input, but for actually truly actuating on the plant, right? I could decide not to have it there also, but it will make my algebra a little easier, at least for now, right? And just like terminal cost. Again, so zero-sum game, dynamic zero-sum game, right? Again, very simple. I'm assuming that at every time step, the attacker and the jammer both, the attacker and the jammer are the same person. The jammer and the controller have access to the state of the plant, so feedback strategies. Right? And again, the jammer is maximizing this, and the controller is minimizing this. Zero-sum game. Okay? So how do you solve that type of dynamic game? Well, somehow you will have to solve Hamilton-Jacobi-Bellman, right, which is kind of dynamic programming, but with a name soup and soup-inf, rather than just name or soup, right? But in this case, I have a constraint here that couples all the different time steps together, because this is not pointwise in time. This is over the entire horizon. So how do you handle that? You typically introduce a new state that keeps track of the number of time you jam, or the number of jamming opportunity that remain until the end of the horizon.
What could you dualize it?
You could dualize it too.
I just add a cost and then.
You could dualize it too, but then when you're solving because I'm solving a game, right? I would end up with multiple infant soups together, and I have to make sure that I have no gaps there. But that would actually work in this case. But we're solving. That's not the route we took here. We just introduced this new state, right? And I just, in this case, will solve Hamilton-Jacobi-Bellman over this extended state space where T is the number of time step until the end, and S is the number of jamming opportunities until you run out. Okay? So, and again, remember, everything could be randomized a priori. The jammer could randomize his actions, right? And so could the controller a priori. And my question is, do I have a settled point equilibrium? And if so, what does it look like? We go ahead, solve Hamilton-Jacobi-Bellman, and this is what you get out of it. So let me go through this. So saddle point strategies do exist. Okay, not too shocking, but true. That is in soup and soup inf at every time step. All right. What's maybe more interesting and actually surprised us a lot and motivates a lot of what's going on later in this talk is that the jammer does not randomize. I did not rule that out from the start, right? He could have, but he doesn't. More precisely, there's a threshold function here, which we can characterize, such that if the state is small, you let it go. If the state is large, if the state is small, yes, that's correct. If the state is small, you let it go, because while if the state is large, you block. How do you think of that intuitively? If the state is large, and you let the controller control, you get, how do I say that properly? If the state is large, letting the controller control reduces your cost in a large fashion. Is that clear to everyone? If your state is small, whether or not I let you control doesn't really matter. It doesn't really affect the cost because the U won't be that large anyway. But if the state is large, there is a big difference in cost between letting you push the state towards zero So that's why it makes sense that you let the message go through. If x is small, well, you block when it's large. The other thing that's interesting is it's not true necessarily. Maybe I should have started with that. Maybe you would have said, oh, something that seems natural is I start jamming, right? And I just jam until I run out of options, no matter what the initial condition is. That's not the solution. There is always, even at time 0, a portion of state space where you don't want to jam. And it's also not true that you necessarily, when you start jamming, you necessarily keep jamming for the next time step. So it's slightly counterintuitive. Okay? The other thing is the control policy is nonlinear. Okay, big deal. In many cases where the control policy is nonlinear. For example, if you were to control over a non-malicious channel, just a stochastic channel, and you're trying to minimize the quadratic cost, the control policy is also nonlinear. But notice that it's a different one. It's not the optimal, the equilibrium solution of the controller. Well, you can't notice it because I didn't formula, but you have to take my word for it, that it's nonlinear and it's not the same, for example, as trying to control over the average channel or anything like that. It's just something different that comes out of HGB. Okay? And the fact that the value function is least-square quadratic, that's not shocking. It's a switch system, and it's a linear switch system after all, right? But so what do I want you to take out of this particular, again, fairly natural, simple example is you allowed your controller, oh, okay, I'll go back to that. You allowed both your controller and jammer to randomize if they want it. What you get out of it is the jammer does not randomize, right? And it's this dichotomy. At every time step, you check a threshold, and if you're smaller than the threshold, you don't do anything. If you're larger than the threshold, you block. Right? And this is what the threshold typically looks like, and we can prove that it's symmetric. We can prove that it has a limit as x becomes large, and we can compute that limit. So it's mostly bell-shaped. Okay? Granted, the region in which you let go is fairly small, because look at the range here, right? That's between -50 and 50, and this is between 1 and 2. So if you compare x to that, it's very small. But it's not the empty set, right? There is always a small portion of the state at every time step where you will block, where you will not block. Okay? So one model, some prediction, and again, what's slightly surprising here is packet drops are deterministic. Why is that surprising? Because if you think again, if you've studied a little bit of network control system or read that literature a little bit, that's not how you think of a network, right? Networks drop packets stochastically. They don't deterministically decide to block or not block, and they don't just do it based on X, right? Maybe they're all or nothing. So if you believe that prediction, that would say, well, strategic jamming is really different from just innocuous channels. The strategic channels are really not like packet dropping channel. And while that could be good or bad depending on how you look at it. Maybe that's good because you get a signature out of it. But if you're the attacker, maybe that's not so good. Okay. One prediction. Model number 2. So model number 2 came from specifically that point, that somehow we were feeling a little uncomfortable with the fact that the prediction we got were deterministic. So we're thinking, well, what if instead of deciding specifically whether to block a particular control input or not, the jammer decided which channel to oppose to a particular U. And then that channel realizes and may or may not block the U, right? So you could think of your jammer, instead of controlling the channel itself, as just controlling an automaton that switches between channels. And then this channel just switch whichever way they might. Okay? Then, in that case, you think that at every time step at the very least, you'd always see a conventional channel, right? Something that does randomize. So maybe if you wanted to capture some notion of stealthiness or have something that looks a little more like the channel you kind of expect, maybe that's a more reasonable model. And for those of you that are a little more inclined, a little more information theory inclined, that may remind you vaguely of the ABC model, the arbitrary varying channel, which of course we're using in a completely different way here, right? The ABC, the idea of the ABC is kind of similar to what we do in robust control, right? It's in robust control, you have a system that you don't know how to model very well. You could, or it would be too complicated. So instead you cover it with uncertainty balls, right? And you say, I don't know which system I have, but I'm going to design something, design a control law that works well for the worst case of all those balls, right? What you do in the ABC, you say, I don't know this channel, it's too hard for me to model this precisely, I'm just going to say design a coding scheme that works for the worst case over all possible switching sequences of an automaton. Same idea here, except I take this literally. I really think of a jammer as a switching automaton. It's not a modeling device here, it's the truth. Okay? So, if you like, the picture is really this. In this case, we're considering, in that second model, you have the controller, you actuator, and the jammer, based on the state of the controller and the state of the plant, decides which channel to oppose to you. If you like math, formula a little more than pictures, let me just tell you what I meant here. So, your jammer has a bag of channels, n channels in there. Each channel is a binary, not necessarily symmetric channel. It can switch between 0 and 1, right? So that's the state of each channel is just in 0, 1, and you have a probability of becoming passing given the current state. And I assume that I've ordered my channels in ascending orders of probability of becoming passing, right? And what does the jammer do? Again, what is a jammer strategy? It's a randomized map that maps the state of all the channels and the state of the plant to a label which says, this is the channel I want to oppose to this particular view. Okay? Then once you're chosen, the channel realizes, and that's what gives you the B matrix that you see in your plant. Everybody with me? Okay, fairly easy. Again, scalar, but that's all I can handle at this level. Okay, so that's what the jammer does. And what does the controller do? Well, the same thing as before. He's trying to control the system with this switching B. And what's the cost? So let me get into the cost just a little bit. And this is even for a one-shot problem, right? Again, I'm trying to build intuition for things that I can solve by hand and get qualitative things first. So one shot. I start from the initial condition and then just transition once. So I have a stage cost again, which looks exactly the same as before, and I could, just as before, put the B here or not. That's what my square bracket is supposed to mean. You can put it or not. That doesn't change the qualitative result here. And of course, I need to penalize again, right? I need to penalize switching. Since I'm doing one shot, that doesn't really make sense to say you can only switch that many times in the horizon, because my horizon is 1. So instead, what do? I penalize the probability of switching from the initial state. Right? Remember, the jammer has a randomized map, right? He picks each of the channel, he picks channel J with probability Pj. So here, the jammer, right, wants to maximize this, wants to maximize Pj0. That is, the jammer doesn't want to switch. The jammer is trying to stay stealthy, right? He would want to leave the channel what it was at the beginning. However, the controller wants the opposite. He wants the jammer to reveal himself. Okay? Or, if you don't even want to think of what the controller is trying to do, that's a switching penalty. The jammer doesn't want to switch. Just to capture the same idea as before. Okay? Hopefully, this is also fairly natural as a model. Okay? In the automaton, slightly more complicated, but it's still fairly natural. Okay? What predictions do you get out of that? Don't read the details. Who cares about the details? Just the thing that matters here is there's 3 rows, not 2. What you see is if your state is low, right, you don't switch. If your state is high, you switch to the most blocking channel. Okay? But most importantly, compared to the first model I presented to you, there is a buffer region between the two where you will randomize. you will pick the most blocking channel with probability P1, and you will pick the original channel with probability Pj0. And you can compute them. Okay? So starkly different prediction. Now there is a region in state space where you will randomize. Of course, built in the model is the fact that at every time, no matter where you are in state space, in planned state space, you see a bona fide channel, right? Something that stochastically drops packets. That's more or less by design. However, of course, in the region where you're randomized, you see a channel that wasn't in your bag from the start. You see a new composite channel, which is randomized between the other channels, right? So which is it? I have two models. The jammer that randomized them. I have two models. They're both fairly natural, if I didn't do too bad of a job convincing you that they're a thing you might want to study. And they're very different. One case, your channel is completely different from what you would expect. It's not a stochastically packet dropping channel, right? The other, it is in some regime. In others, it's a non-standard channel. And most importantly, there is this buffer region. Which is it? Well, to try to understand a little more how we could explain those discrepancies and understand them, we do what theorists do, we make things more abstract. But only slightly more abstract. Let me just, this is what I'm doing. I'll go back to the equation in a second. What I'm doing basically by making more is, I'll go back to the previous picture I showed you, but I consider my network or my jammer to be able to control just a more general automaton than my channel switching automaton. Just something slightly more general, right? General automaton. What I had before is the states of that automaton with different channels, and basically you could not even transition from one to the other. You would just look at what happens and just choose one of them. Okay? So that's how I'm more abstract or more theoretical. I'm considering the controller is trying to do the same thing as before. The jammer now is just controlling a discrete automaton with a readout map. Okay? So, again, if you like formula a little better, this is the plan just does what it was always doing. And it has a cost that only depends on the state of the plant, but not the state of the automaton. What does the jammer do? The jammer controls the network, which is this discrete automaton, which has, of course, a stochastic kernel of its own, and a readout map. And this readout map takes value in 0, 1, depending on the state you're in. Okay? Everybody with me? This is the slightly more arid part of it. It's just two slides. Right? But everybody with me? Okay? And this is the coupling here. That is the input that is seen by your plant, Vt, is just this epsilon t times the actual u that's being sent, where epsilon takes value 0, 1. But now it switches according to this control Markov chain. Okay? And if you really want to be pedantic about it, you can rewrite the whole thing as just a bona fide zero-sum stochastic game over extended Born spaces. And it just makes your transition kernel slightly more complicated. And the reason why it looks like this here, my transition kernel, and if you're really reading this, is because I didn't put any noise in my plant. So of course, the only transition that are allowed on the plant are the transition from x to x prime only if x prime is exactly ax or exactly x plus bu, depending on the value of what the jammer did. Of course, if I had noise, I'd not have different. Okay? So, details are details, but the idea is, again, this. I'm considering a more general class of zero-sum games where the cost is the difference between both the jammer and the controller have cost. If I want to create a zero-sum game out of that, I just subtract them, right? They want to min-max the difference of the two. The controller controls an LTI system. The jammer controls the control Markov chain. Okay? What happens? What are the equilibria generically? What happens in general? In particular, the question I'm after, since I see those very two different predictions, is when does the jammer ever randomize? do I expect to see this buffer region when randomization happens? And if so, what kind of randomization happens? Okay? Well, it turns out that we can characterize that exactly at every time step when the jammer randomizes. So, where does that come from? So, let me just go back. Sorry. Come on. Okay, so this is my, the payoff function, and of course I'm solving the zero sum, so I'm going to, what the jammer is trying to maximize is the expected value of this cost, and what the controller is trying to minimize is the expected value of this cost too. You write that out, take the stochastic kernel into account, and you get something that at every time step of your HGB looks like this. Right? This F sub t, that's horrible notation, but what is it? It's, if you think about it, the cost to go of every entry I of this big vector here that depends on you, is the cost to go plus stage cost corresponding to the pure alternative I, the pure mode I of the jammer. Okay? So what I have here is an expectation. May not look like it, but it's an expectation the same way. Expectations are linear, right? So your zeta here captures the probability of choosing each alternative, and this vector here is the cost that corresponds to this alternative. It looks horrible, but that's really all that's going on, right? The jammer is supermising over this simplex, and the controller is just minimizing over all possible regions. Everybody with me? At least conceptually, you can do this too. It will also take you 10 minutes. 5 minutes. It took me 10, so it should take you 5. Right? And at every step when you solve HGB, you have to make sure that this one-step gain has a value so that the insup is super. Okay? But basically that's what I have. I've reduced all of these problems at every time step as something that looks like this. If I write here, can everybody see it? At every time step, you really don't like people to use the board.
You actually want to go find a marker.
Oh, well, maybe that would be necessary. Again, so at every time step, you reduce this into a bilinear, right? The insup of a bilinear form. That's really what you have, right? Did you get a marker? No luck? No worries, okay. So that's really all there. Okay? So, simple, very, very simple question, not even a Q exam question. If you forget this inf for a second, right? You're trying to soup something like this over zeta, right? You're trying to soup zeta transpose F for zeta in the simplex. What do? You put everything on the max entry of F, right? That's the water filling that it's almost insulting to call water filling, right? You fill just one glass, right? But now the question I'm interested in is, when do you randomize? When does that not happen? When are you not at just one single vertex? So of course for that to happen, necessarily, you need at least 2 entries of that vector to be equal, right? Otherwise you won't randomize between them. Okay, but that's not enough. In fact, you can rummage through Stephen's books a little more, and what you'll see is you basically need your U to be a Pareto point. You can prove that exactly. That's nice. That's basically a separation of convex set type of argument. So what you get out of this is basically a theorem that's like this: that you will randomize if and only if. So the equilibrium solution to this zero-sum game is a randomized zeta, corresponds to a randomized zeta, if and only if there is a U for which at least 2 entries of your vector F are equal. For every other U, there is at least 1 entry of that vector value function that's strictly better. That's the Pareto condition. That is, if you're not at that point, there is one that's strictly better than you, right? So you're not Pareto. And this U is not the minimum of any one in particular, right? That's basically the condition. And that's it. That's an almost converse. If you really want to deal with this case, you have to work a little harder. Okay? So in picture, what does that mean if you were to do it in dimension 1? If your U were dimension 1. So these, what am I drawing? This is, let's say you have F1 and F2.
I'll take the marker.
Oh, right. Sorry. Thank you so much. Right? So I have zeta transpose F, and this is a 2 vector, so just F1, F2. Okay? And what I've plotted here are F1 and F2 as a function of U. Okay? So what this says, and I want to know when is the inf sup equal to the sup inf at a non-pure zeta, right? So these are the good cases. So that's F1 as a function of U, F2 as a function of U. They intersect, and the derivatives make an obtuse angle. The tangent make an obtuse angle, which means that if you take any point that's not U, there is at least one of the function for which the value is strictly less, right? This is okay. This is okay. If they cut at the minimum, they both have to be at the minimum. None of these is okay, right? This is not an obtuse angle, really, right? This one is at its minimum, but not the other one, so that's not okay. And this one is constant, so that's also not okay, right? So, of course, why did I formulate the theorem without any assumption of convexity? Because remember, I want to apply that at every time step, right? And the value functions, which I expect to be piecewise something, may not be differentiable everywhere. So that's why I need the previous formulation of the theorem, not assuming differentiability. But if you're differentiable, these are your conditions. That's if and only if. You have the saddle point is at a randomized vector if and only if this happens. Okay? And that goes up, again, in higher dimension as well than just for the picture. So going back to that, what can I say? Well, I can say two things that are of value to answering the main question that motivated this, which is what does a strategic channel, at least in this framework of ANC game, look like? Well, first thing is, okay, example 1 is really a corner case. You should not expect to see a jammer that does not randomize. Example 2 is generic, not example 1. Why is that? Well, remember what your stage cost was in example 1? I said it's xt squared plus alpha t ut squared, right? And I just said, okay, I just made this choice because it makes my algebra easier. That alpha t, right, that you only pay the u when it reaches the plant, not when it's created. And at that point, it looked fairly innocuous. Turns out that it's not innocuous at all. Why is that? Because if that's your stage cost, when your jammer actually blocks, the cost to go at that point does not depend on you, which makes sense. If you block, no matter what u is being sent, it doesn't matter, it doesn't affect your cost. So if I'm trying to plot what my f vector looks like in this case, it looks something like this. I have one which is nice and quadratic, or no, it's not quadratic, it's convex. But the other one is flat. It doesn't depend on you. That's a case where I don't have a randomized saddle point. This is why I don't randomize. It's specifically because there is one option in which whatever the controller does, the jammer doesn't see it in its cost. Again, I'm not doing anything difficult here. It took us a little bit of time to understand how to put them all together and understand what came out of the description of this model. But so this is to say again that for example 1, this is what's going on, and that's not generic, right? Now, if you're asking what is generic, well, this is what's generic. And I mean generic in really in the proper mathematical sense, right? That the set of parameters for which that happens is co-meager. That is meager being intersection of open set. Right? What's generic is that you will always get this buffer region. There will be region of states of the plane state space where the jammer will randomize and others where it won't, and it will alternate. That's generic, right? So you will get weird channels, but not everywhere in state space. Okay. The other thing that's generic is that, and this I should be in 1D. That in general it's more difficult to characterize. But in 1D, if your U is 1D and your X is 1D, which is all I've been talking about here, when the jammer randomizes, he randomizes only between two alternatives. Why? Because again, generically, all of this happens at intersection of curves. Generically, curves intersect. When you have intersection between, even if you have n alternatives, they intersect 2 by 2, generically, right? Because anything that's not like that you can perturb, and you only get 2 intersections. So even if the jammer has a lot of possibilities to a priori randomize, generically when he does, you only do it between 2. So that puts a bound on how complicated this weird adversarial channel can get. Okay? So we're currently working on making this generalization to multidimensional system clear and crisp, which I don't quite have just yet. It's still true that even in higher dimension, even for multidimensional systems, the randomization takes place in the lower dimensional. Uses only a strict subset of what's available. Exactly what you have to look at what the possible corner cases of that LP look like. But bottom line, that's what comes out of this analysis. So hopefully, just to conclude, what came out of this presentation, hopefully, is that even simple game models of cyber attacks in control system can have subtle prediction. You have to be careful. The specific modalities you put in your model matter. Sometimes you think you're doing innocuous, you're putting innocuous assumption, you're getting weird results out of it. Well, that's because, in fact, that was not innocuous, but that may be hidden. Also, the information structure matters. I only took about one type of information structure here, where everybody knows everything, because that's the simplest. But we've solved other cases where for example, in example 2, where the jammer has access, must act before being able to observe anything of the plan. Right? And that matters. The qualitative prediction is the same, but of course everything else changes. The shape of the cost to go changes, the regions where you randomize change, etc., etc. So that also matters in game, the order in which you play, and who knows what at the time which you play. And the question again is, so the result is we get some kind of generic characterization of what adversarial channel can look like. The other thing we're also looking at now is whether that can be exploited, maybe even asymmetric information game, where now I know what to expect. I know what kind of behavior I should expect from you under some assumption. If I don't observe that, maybe I can infer that you're not being strategic, but of course you know that too. So there is a way to capture that in the framework of the asymmetric information games. Things get a little hairier, but we're working on that. And I think that is indeed my last slide, and I'll thank you for your attention.
Questions? A couple. So the first question was this: if you wanted to do practical control,
right,
you would use MPC.
Most likely.
Yeah. You would.
Yeah.
Now suppose you wanted to do a practical version of something that's robust against, and let's suppose it's the first example, which is the attacker can limit your the availability of the actuator.
Yeah.
Right. So let's take that one. You could easily set up some kind of min-max type thing. Mm-hmm. And is that what you would do? Do MPC with some min-max thing?
You could definitely look at that.
You see what I'm saying? So you're at a current state.
Right.
You would simply plan out your horizon worth of actions, but you would also plan out the attackers with the constraint built in and solve that min-max problem.
You could do that, you would get similar.
I think you would.
The issue, though, is why would you necessarily assume that the jammer has the same horizon as you? And
when you use NPC, if the horizon matters, it's not going to work anyway, right? I mean, that tells you you're not doing NPC correctly.
So, okay, do you mean that they're both doing NPC, or you're doing NPC just because?
This is from the point of view, I'm operating a plant.
Right.
All I know is somebody, I don't know who the hell they are, and they have the ability to block my access to my actuator.
Right.
And now I made some assumption, which is a bit weird, but let's suppose I make the assumption they can only do it 15% of the time.
Right.
Let's say.
Right.
Okay, so I decide to plan out 50 steps ahead of time.
Mm-hmm.
And if 50 is a parameter, we're in deep trouble, right? Because if it's done correctly, it should work for 30, and it shouldn't be much different if I take that to be 200, right? So I don't think that's an issue. And all I do is I say I'm going to plan out 50 steps, but I'm going to solve a problem which is to minimize, over my action U, the max over alpha of that cost, and then I'll take the first step. So I'm not assuming anything about the attacker. The only thing I'm assuming is that in the next 100 steps or so, they can.
But the next 100 real steps, not the next 100 planned steps.
Yeah, the next 100 steps, they can only block me 10%. I mean, I don't know where that belief came from, but let's suppose.
Right. No, we've done something. We've done a receding horizon version of this, where basically you exactly as you say, you slide your window and you re-implement this every time. Mm-hmm. The question, under some assumption, you still get stability of your system. In terms of performance, that's harder. I don't think we have a clean result from that. But if you only care about at least guaranteeing stability, you could do that. Yes.
Well, let me ask another question, which was, I mean, there is something weird about that, right? Because you have to make these assumptions, and why on earth would you make an assumption like that, right?
Right.
That they're gonna. I mean, you sure as hell don't know that parameter.
Right.
Right. So, but let's go along with that and pretend that makes sense, which is fine. In the first thing, the intuition is very simple. That if the attacker is resource limited, they won't block your availability until you're vulnerable, and that's when your state is big. Right? So what it suggests is that if your original objective was like quadratic, you really should replace it with a super quadratic objective. Mm-hmm. The reason being that when you're small, no one's going to go after you.
Right.
But when you're big, it's not just that you'll run up a quadratic build, but an attacker will be lured out of the bushes, and you'll actually end up. So all you would need to do there is to make a super quadratic cost function, and wouldn't that give you a control that was now more robust to a resource-limited attacker? I think in the end, that's all that really happens. No, I don't want to say all, but that's.
The general insight that there's this threshold, and when you're vulnerable, you're being attacked. That will be there no matter what.
And that I think that's equivalent to having a super quadratic, or it's very close to having a.
So that's a good point. I haven't thought about that, but that would be very interesting if you could basically ask the question the other way around. That is, if you let's say you have an actual cost that's a real control cost that you're interested in, but you expect that you might be attacked.
And you'll be attacked when you're vulnerable. If
so then you should change your cost. You should pretend that in fact you're interested in a different cost and solve for that, and see what robustness you get for the basic cost you want. I haven't thought of that, but that should give you something. Yes, that's a good point.
Because that's kind of what would happen here, right? They have a threshold. Mm-hmm. You would lose so the value function becomes super quadratic.
Yep.
Or sorry, not super quadratic. It'd be quadratic. You'd have the quadratic base one.
Yep.
And then it would grow faster all of a sudden because you'd be open loop occasionally because.
That's right. That's right. the difference. I mean, that is what you do in the end, right? I mean, that when you're solving that same
right,
soup
you didn't show the control. When you said it's not LQR, but I presume it looks like a control that is for a super quadratic cos. I'm just guessing that.
Well, it has to look, when you do your in soup, right? I mean, that's basically the same thing you get when you dualize something, is you are minimizing the cost plus the penalty, right? That corresponds to whatever the penalty that came from taking the inner soup, right? So it's a U that minimizes the cost. Now, most likely, I should go back and look, most likely that cost is super quadratic, you're right. But I never went back and specifically looked. I mean, so 2 points. Yes, when I said this is a weird U, it's a U that's the optimal control for some cost. That's true.
Oh,
right.
So that'd be interesting to know what that cost is.
Exactly, that's the second point. And
but in the general case, that should be something like the original cost plus this the addition or some product or whatever the hell it is should be interpreted as a vulnerability cost. Right. Something like that.
Yeah. So that
I guess something like that would happen, right?
So then I want to go back and actually do what you said, which is actually dualize it, dualize the constraint directly, and see if you get a better expression of that cost in this way. Because you should get that, right? That again, that's what you get when you solve zero-sum king. You are dualizing something. So these are good points. Yeah, thank you.
Yeah, it may not be that you can't express it that way, but at least approximately it looks like
Approximately, yes.
Yeah.
Do you have any intuition as to what the optimal controller does?
So, let me see if I have a slide for that.
All you said on the slide
It
was
is
not
non-linear.
LQR.
It's not LQR. It's not control over. I mean, there are results in the literature, right, that are even, I think, dating back to the 80s, of even what it looks like to control over stochastic B, when you know the actual distribution, and that's also nonlinear, and that's also not that. This U, RU, is also not that. It's also not the optimal U corresponding to jamming, to controlling over stochastically bucket dropping jam. What it looks like.
If you have random A or B, then for sure it's linear, and I mean if they're like if the A's and B's are
If they're independent, yes.
Yeah.
But in this case, it wouldn't be because they're conditioned of.
Oh, of course, right. But I'm talking if they're independent, they would.
If they are independent, yes. Yeah. So
And just so I understand, here the controller depends on S.
correct.
So it depends on the history of the attacks that you've seen.
On the sufficient statistic of that, which is just how many times I've seen you jammed up to now. Not the full history, actually. It's a strict subclass. It is when you jammed it in the past is irrelevant. It's just how many times you jammed. That's right. So I wish I remember exactly how that U looked like. I mean, clearly when it's locked, it doesn't matter. That's indeterminate. I know we plotted that at some point. I just should have included it. I don't remember it on my head, but I can try to find it offline.
I'm sort of worried about because the story doesn't really. It'd be very hard to explain to someone how it is that you can competently make the assumption the attacker will attack you only 10% of the time. So, whereas in fact, probably something where you could is this does suggest that if you were a jammer, it suggests that the right thing to do is to wait until someone is vulnerable. So that's where there's only one action the jammer can do, which is turn on.
Mm-hmm.
The total number of attacks being 1 is perhaps a sense.
Right, but it stays on. Right. So.
Right.
Well, it could then go to a random thing.
I mean,
If you can attack once and figure that, well, someone's going to notice that you attacked them and they're going to.
Yeah.
So, I mean, I'm not, again, this was this specific form of the constraint was done for tractability, right? I'm not necessarily wedded to this particular form. You could think that you have an attacker, if you're thinking of physical jamming, you might have something that's more a physical constraint, right? Your resource constraint in the power you have in there. So that wouldn't be in the number of times, but you could, find a guesstimate of how much it costs every time you jam and turn that into some constraint on it like this. So power limited jamming, that's fairly reasonable in military context. Not necessarily in cyber attack context. That's really that is truly a hit that I'm willing to take. Why does it cost you anything to block? Or even if you go at the level of opening a packet and tampering with the data, what does that cost you, right? What is a good measure of that? So that
could probably make a better model of a distributed denial of service attack, right?
You could.
Because the model might go like this: that the one action you have is to turn it on. So you turn on all of your bots or whatever, and now they're pumping packets at your actuator.
Right.
Then some reaction is going to happen, and after a while, it'll take a while to build up the table of IP addresses to block and things like that, and then spread that out to the routers and stuff. So you might be able to make some kind of dynamic model
where you're on for a while. I mean, the other model that we have started playing with, but it's more difficult, is more of a stopping game, right? That is, I don't have a horizon from the start. That is, we keep playing until something happens. Which is kind of more of a model of even maybe power stealing, right? If I steal power from the grid, right? If I do it in too flagrant a way, you'll know and we'll stop immediately. So I need to do it so that I stay on, right? So you could have some kind of safety set, right? The constraint wouldn't be on the attack of the jammer, it would be more on the state. If your X crosses some boundary, everything stops because I just turned the power system off or something like that. So we work on that. But the results are actually they're equally as qualitatively they're all hybrid systems, right? So qualitatively they all look the same. The question is how far can you take your one symbol formula and actually compute them practically? But you're right. This exact mathematical expression of the constraint is really academic. Yes.
Also, I guess the only people who've really done this, it's U.S. and Israel, right? And the instant you take over something, you put a rootkit in, so that what you think is XK is not XK. Immediately, right? And so that's a different model from this, right? And so all your monitoring says your states are fine. I don't know if there's an interesting model you can make from what was actually done, because in fact this has been done.
So you need a picture of a centrifuge.
Oh, well, you want to see some? Actually, I forgot to. So this is Aurora. That was actually tried by the U.S. on the U.S. in 2007. That's so that's cyber attacking.
This is SCADA.
Yeah. So the beauty is you see nothing until the thing just starts fuming. So I don't know if you actually have that there you go. And now that's just done. So I don't know if in this particular attack, all your sensors just said everything's fine or not. I don't know. Presumably, from what I read about Stuxnet, that was the case for Stuxnet.
Right? I think that's traditional hacking. Rule number 1 is install a rootkit.
Right.
Not that I would know personally.
Well, that's also the point when you said Israel and the U.S. are the only place.
They were actually, it was the number of jams that actually mattered, right? It was only when you saw a certain number of sensor users fail that you said, oh, something must be going on. Even
Exactly.
we're saying to write it. But so in that case, M is actually the right parameter.
But in that case, you're not attacking that. That's an M on the other
Right, it's an M on
sensor
it's
attack,
on,
not
it's
exactly.
an M on the number.
So that's something also
Well, it's an M on the number of centrifuges that fail, right? So it's an M on the number
of sensor on your
push
centrifuge.
too far.
Well,
The number of systems that you push beyond their operating.
Yes.
But, yeah.
It's the dynamic one we find how many errors can cause before they cause.
exactly. So that's this stopping thing that I don't know a priori. I just know that at some point, whoever's in charge will notice that something bad's going on, and then I better have done all the havoc I wanted to at that point. Right. Exactly. I mean, something else we're playing with. I was telling Sanjay about that falls under the heading of, I guess, cheap talk of sorts is what if I'm trying to spoof measurement. I know you have a measurement algorithm, you have some kind of estimation algorithm, and I know what you expect to see, and I'm trying to relay wrong measurement to you. I'm a strategic sensor, and I'm trying to relay wrong measurement to you so that you think everything's fine when it's not. I mean, people at KTH, I'm sure you're aware of, have looked at that more on, under the corporate sensing umbrella, but not strategic. Not the fact that I know what you're trying to estimate. Looking at that too. But as I said, this was DOS-ish.
Yeah. So just to ask us another abstraction question.
Yeah.
Stephen said you should be attacked when you're vulnerable. I'm just thinking about the control system in a car. The point which you don't want something to take away your control is when you're either trying to accelerate hard or when you're trying to brake hard. Do you have a general statement of when you're vulnerable? Or does this allow you to attack that problem in some way?
I guess. I mean, if I go by what you just said, that has something to do with how critical that particular control input is to your system.
Yeah, when you're just cruising along, you don't really care if somebody turns off the engine.
Right.
You're trying to brake hard, and the brakes and you fail, that might be a bad time.
By the way, you
Yeah,
think
why
you're
I
talking
know
about
that.
something. You think you're talking hypothetically, right? I was at a workshop in DC a few months back where somebody talked about that not for cars but for trains. Apparently, that has been tried and worked very well. Jamming the train when it brakes, and the inertia is so large that you don't even need that much bandwidth. You just need to lock a little bit at the right point. So that's not your question. I mean, that has something to do with, again, the criticality of that particular control input, which I would relate to, I guess, the value of the cost to go, or something like that, which is what comes out of this. I don't know if I have anything intelligent to say past that. If you want, I can sit down.
Right. Well, we should thank Cedric.
Thank you very much.